In June 2025, a gardener in Ōwhiro Bay, Wellington, was doing something completely ordinary. They were gardening when something extraordinary happened. They came across human remains. The police were called, a forensic team came to lock down the property, and a potential crime scene was established. Flip over to March 2026, and results were released in the media to confirm that this was not a recent murder victim or a missing person. They were the remains of an ancestor who lived 300 to 400 years ago in the 16 to 1700s.
And therefore, likely a tupuna Māori, a Māori ancestor from Te Ao Tawhito, pre-European times.
But how do we know this? How can scientists look at the remains of a living thing and say when it was last alive? Well, the answer lies in a process involving cosmic rays, tree rings, radioactive decay, and a clock that never stops ticking. Tēnā koutou. My name is Dr. Isaac McIver. I'm an archaeologist at the University of Otago, and this is the past before us. Today we are discussing radiocarbon dating, how it works, whether it's reliable, and how archaeologists use it to tell time.
This story starts in our upper atmosphere.
Cosmic rays come into our atmosphere and strike atoms, causing microscopic fireworks, chemical reactions. One reaction involves nitrogen being struck by neutrons and turning into carbon-14. Now, there are three forms of carbon. Two of them are very stable, carbon-12 and carbon-13. Carbon-14 is a radioactive atom, meaning it is unstable. It cannot stay forever in its state and eventually wants to return back into nitrogen-14. Now, carbon-14 rapidly binds with oxygen in our atmosphere, forming carbon dioxide. Plants like these trees below me take in carbon dioxide through photosynthesis to generate energy. Plants don't really care whether the carbon is unstable or stable, whether it's carbon-14 or carbon-12. Through the food web, that unstable carbon finds its way into all living things. Yes, that means that you and I, these plants, everything living on Earth right now has radioactive carbon-14 in it. While these trees are living, they're constantly taking in carbon dioxide, constantly refreshing their amount of carbon-14 that is then slowly decaying back into nitrogen-14. So why is this ratio between carbon-14 and carbon-12 important in archaeology? Well, too close. The answer lies in when things die and stop taking in carbon-14. You see, when organisms die, they stop taking in carbon-14. And without that constant replenishment of carbon-14, the amount of carbon-14 in the material of that living thing declines. So in this case, this tree has had its last days. These pine needles, although some of them are still a little bit green, they've stopped taking in carbon-14. That's basically locked in the proportion of carbon-14 to carbon-12 in every cell of this plant. Now, that slow decline in the amount of carbon-14 is the key to radiocarbon dating. Okay, so we know that carbon-14 declines at a steady rate. This means we can measure the ratio between carbon-14 and carbon-12. This is because the decay of carbon-14 acts as a clock. Okay. So here we have a series of pine cones representing the full amount of carbon-14 in a living organism. Material forward. So that's 16 pine cones. When a tree dies, say, it stops taking in carbon-14 from the atmosphere, and this is the full amount of carbon-14 in all of its cells, in its material. Okay, after one half-life of carbon-14, which is the time it takes for half of carbon-14 in a sample to decay back into nitrogen-14, half of the 16 pine cones here will be removed. This takes 5,730 years. Another 5,730 years would be another half-life, so half of the remaining pine cones would be removed. Over another 5,730 years, half of the remaining pine cones again would be removed, and so on.
If we reach 8.7 half-lives, that's the equivalent of 50,000 years after the death of the organism. By this point, there's only 0.3% of the total amount of carbon-14 in the material of the organism. This is such a small amount that radiocarbon labs can't accurately measure the proportion of carbon-14 to carbon-12, and 50,000 years therefore serves as the approximate limit of radiocarbon dating.
Say you have an artifact out of an archaeological excavation and you want to know when the organism that was made into this artifact died. You can take a sample, send it to a radiocarbon lab, and they'll look at the proportion of carbon-14 to carbon-12, and they'll be able to estimate when the organism died that was then turned into this artifact. Now, the incredible thing about radiocarbon dating is that the proportion of carbon-14 to carbon-12, even in the atmosphere where it's most abundant, is about 1 in 1 trillion. If you start counting each second, it would take you 31,700 years to reach 1 trillion. So one of those seconds across those 31,700 years would be carbon-14. The remaining seconds would represent carbon-12. That's the amazing science that goes into carbon dating, where radiocarbon scientists are able to locate and find that carbon-14 and count it in relation to the amount of carbon-12. So, radiocarbon scientists, being good scientists, decided to test the accuracy of radiocarbon dating. And what they did is basically found another data source. In some cases, they used trees. Here's a beautiful example of a tree that has died, unfortunately, where you can see this beautiful display of growth rings. Each growth ring in this tree represents a different calendar year. If we were to count each growth ring, we would be able to say, just by looking at it, how old this tree was when it died. So we can do that now. 26 years. Now this is a pretty big tree. This is a pine tree. It fell over in a storm and I've just been chopping it up. But in some areas of the world there are enormous trees, like massive Cody trees in Northland, that span hundreds of years. Radiocarbon scientists have taken overlapping tree rings from large trees as well as other sources of information like coral to create these long-term calendars going back thousands of years. Now what radiocarbon scientists did is that they took samples from trees like this, either individual tree rings or intervals across tree rings, radiocarbon dated those individual rings to see what the relative proportion of carbon-14 to carbon-12 was. And what they found was that it fluctuates through time. That means that the amount of carbon-14 in the atmosphere, in the air that these trees are taking in through photosynthesis, is actually variable through time. That means we need a calibration curve to correct for the variation in atmospheric radiocarbon. So, big radiocarbon calibration curves have been established for different regions of the world, based on radiocarbon dating individual tree rings and other sources of information like coral. The tricky thing about the calibration curve is that it's really wiggly. There's a lot of fluctuation in the amount of carbon-14 to carbon-12 through time over tens of thousands of years. This means that sometimes if we radiocarbon date an artifact and it has about the same ratio of carbon-14 to carbon-12 to a period in the calibration curve that has either a flat area or several wiggles in it, that means it's going to result in a really imprecise date. Can sometimes span 150 years, 200 years or more. So if you see a radiocarbon date that spans 100, 200 years, it's not because the archaeologist in the radiocarbon lab are being vague. They're reporting how accurate we can be for that artifact at that point in time. So, what can we date? Basically, any organic remains. Really common ones, charcoal. Charcoal, burnt wood that preserve very well in archaeological deposits. Excuse me, Tuku. Don't mind me. Hang on. Another key material used, shell. One issue with shell is that obviously shells don't photosynthesize and get their carbon from the air, from the atmosphere. They get it from the marine environment around them. It takes a little bit of time for the carbon-14 to get into the marine ecosystem. That means there's decay in the carbon-14 before it reaches the shell. And as a result, marine carbon-14 is often slightly older than terrestrial or atmospheric radiocarbon. And that means we have separate calibration curves for materials from marine sources to those from terrestrial sources. Obviously, we've also talked about human remains, bone, hair, any remains of living things can be used for radiocarbon dating. So June 2025, landowner goes gardening, comes across human remains. Police called, property shut down. Turns out those human remains are from 300 to 400 years ago in the 16 and 1700s. How do we know that? From radiocarbon dating. However, this is not a rare case. Radiocarbon dating is the workhorse of archaeological chronologies, not just in New Zealand, but anywhere in the world before about 50,000 years. My name's Dr. Isaac McIver. This is The Past Before Us. If you've enjoyed this show, please give a like and subscribe on YouTube. Check out my website at www.thepastbeforeus.com, where I include an associated written article about this content, which includes explanations and references that you can delve deeper into the story of radiocarbon dating. Tēnā koutou, tēnā koutou, tēnā tātou katoa.